Hello everyone, and please don't make me stay here longer for like 40 minutes or something, because it's impossible to explain everything about bytecode in that time. Especially you will see why later on. Yeah, so coming to my talk. My name is Krzysztof, as Tomasz said, and I'm from Virtus Lab. Virtus Lab is the organizer of this conference. We're doing a lot of fancy stuff, including tooling. We are hiring, so just a word about us. And now a word about me. So I work in Scala for over 6 years now. I work for like almost 4 years, like almost 5. Yeah, that doesn't matter. Around creating a tooling for really huge code bases in Scala. It's like currently it goes like 2.5 million of lines of Scala code, heavy usage of macros, compiler plugins, all nasty libraries you can think of. So there's like a ton of problems. Compilation, probably the biggest, I mean compilation time, but there's other problems, like if you got multiple developers working on the same monorepo with the single branch, that they all match the pull request, you got tons of problems that nowhere else can be seen. Don't ask me why they decided to go for that. My job is just to make it working, and this is not the easy job. Here also my GitHub or Twitter if you are interested, and let's move to the presentation. So slides for this one, if you want to follow, are there. I will show this link in many more places, so you don't have to take a picture or something. And now you probably want to know how stuff like default parameters, or I don't know, self-sync traits, or private modifiers that are not Java modifiers that are Scala like private or this or private or given package are implemented. And this was like the main goal of this talk at some point, but then I realized that probably I'm not the best person to actually to give this talk. I do not invented those things. I probably have to guess why the stuff was implemented in a given way. So probably you need to ask Jason Zaug or other members of the Scala compiler team how the stuff works like that works. So instead, today, I want to focus about other aspects of our bytecode, our code. I want to focus on performance. So I want to ask ourselves like how fast the code that was generated from our Scala applications are. So we will benchmark a lot of stuff. And this is really important. You cannot say that something is faster. Like I have got a feeling that my code is 2 times faster than the other code. Unless you show me a benchmark or multiple benchmarks with different configurations, different data, different machines, then you maybe can say that in this subset of benchmarks, this code seems to be faster than the other. And benchmarking is a really complex process, even the benchmarking per se, or the C application. But if you add a JVM into the mix, and our application, like most of our application on Scala, is running on the JVM, then you got stuff to think about, like, I don't know, JIT that get warmer and at some point stop being warm because it decided that it's not a good idea to be warm. I mean, I saw this kind of things. Rory will tell you more about this kind of stuff, like later on. And with that complexity, I'm not claimed to be an expert in that field. So I will show you my experience and what I get out of that, and hopefully you will agree with me with my results. And there is also one important thing. Whenever I always said that something is slower or faster, it is like a shortcut. What I mean, like in my benchmark, in my current my machine running that day, this thing was faster. It is probably they are faster in all the cases, but I'm only presenting the results of my benchmarks. So, and it's easier to say something is faster. So now you are warned, and we can go further. This is, maybe you can recognize this picture. This is the performance of the Scala compiler. I mean, how fast is to actually to compile Scala P. And after like just about the 2.12 migration, you can see this big spike over here. There was like quite a lot of regression introduced, and Miles haven't found it. So they started to measure the performance, and as you can see, hopefully, like the last part is getting faster. So good. But I mentioned that in my day job, we got this big huge repository that compiles for like almost an hour. and we are blocked by many things because of the fact that the compilation took so long. So at some point, I decided that my free time, I will try to see, I will like benchmark, I will profile the Scala compiler and see where the slow it is. And I was like super excited about that because, yeah, I will for sure find like, this spot, this is slow, this thing, I will fix that and I will be like, famous and everything. And 3 days of profiling and I was like, everybody did what again is possible. There is no such things in the Scala compiler. So then I was thinking, because if you profile the compiler, it's like, I don't know, it's like 400 methods or something that takes, I don't know, pretty much the same amount of time. So if you want to fix that, you will get like less than 1% of the speed up. So I was thinking the other way. Maybe there is like, the general problem with the layout of the compiler. Maybe there is the general problem with the code there that makes it so slow. So in this presentation, I want to ask this question, like in more general term. So I want to ask ourselves if we can write a fast code in Scala, the code that will run really fast. But this is not the code. I mean, I can write any piece of code, but only what matters is how the code is what the bytecode is produced, because the bytecode is running. So if I can write a fast bytecode in Scala, but I don't like to write some whiles loops or other nasty stuff, that is why I picked Scala. So my question is whether I can write a code that is nice, that I like, that I can show on the conference, on the slide, and be like proud of that code. And in the same time, it is fast. And the last natural step to that is how can I do that? So this is the thing I want to look at in this presentation. So as I said, in order to show that something is fast or not, we have to benchmark that. So this is the idea I want to benchmark on. So I got simple trees that represent the skills, and I want to, in the end, what I want to benchmark is how to like compute the sum of the experience required to get all the things in that tree. And for a benchmarking purpose, of course, this is a trivial thing, and I should like it can be quite easily done in a really sophisticated way. But there's one thing from all the things I want to benchmark later on, that the tree is kept. So every time I want to like get this experience, I want to traverse the whole tree. And how I get like the amount of experience required to get for each level is like every node gets its own fit assigned, and each player, like it's, for example, easier for him is to actually learn stuff about dexterity. So he's like more dexterous than the other guys. So the experience is like the cost is less. And the same thing for the strength or the wisdom. So basically, I will got these 2 trees, and I want to benchmark how much time it takes actually to traverse those trees and find the required experience to get all the fits. So this is the player traits. And as you can see, there is this annotation here, compiler control. I'm using JMH, as you might guess, and this is the notation comes from JMH that says that JMH will do everything possible around this method, so that method is not in line. So that method is always invoked. And why I got like method that I don't want to like in line, but just return a single value. So my point is here, I want that those things represent the actual business logic in your application. And in the benchmarking, I want to invoke that method, but I don't want to measure the time that method, how much time that method spent. That is why I want, so that method is invoked, but does not take almost any time. And my trees, as you can see, it's all represented in the skills tree class. There is like 3 for archery and charisma shown before, and it's all wrapped in the something like representation. Why I have to do that? So in order to be able to benchmark stuff like implicits, or especially stuff like type classes, I have to preserve the concrete type. That is why I got this type T that is never used except for maybe in some cases. So this is my definition of my benchmark. I will show you for the few next slides. So basically, I'm running 10 iterations to 200 milliseconds each, and that to warm up the JVM, and then the same amount of iterations, but there's twice as longer to actually measure the time. And I'm using sample time mode, which means the JMH will run the application for the time assigned to given iteration, and then will count how many operation was invoked in that time period. And then based on that, we'll tell you how fast it is. And I'm using forking just to have more stable data. So in benchmarking, there's also the idea about the baselines. So when you run an application, you don't, because you measure many things when you measure time. It's like how much time is required to start, like invoke the method, how much time is required to actually run the business code that is not maybe needed. You don't want to, like, even the methods are really simple, but the times required to run them is not the thing I want to measure. So that is why I got this baseline, and as you can see, maybe you can't see, but you have to believe me that benchmark, like this baseline, what it does is actually run all these methods and sum the results. So it's called like archery, dexterity cost, strength cost at a given amount of time, depends on what tree we are parsing. And then like each of the benchmark will run it like 2 times for each tree and then wrap it in the array and return. This is what all the benchmark does. But in order to prove that this baseline is actually a baseline, so the GT is not like inlining the fit instantly and just giving me 5 every time I run it, I want to show you with the proofs, and this is the results. So as you can see, the first proof that was basically create an array with 4 elements, it's like way faster. They created an array with 2 elements that are static and 2 elements that was like dynamically computed using the baseline. So it's the time, like the time is growing, so I presume that the baseline is okay. And for the all next charts, I will use these red lines, the red line that is here, that represent baseline, so it's like 95% of the baseline run. So, are you ready? Are you ready to see the benchmark of true? Whether it is the ScalaSphere that is inherently slow because of the way it's written, or there is some other way. So, how do you think? How much slower the ScalaSphere like approach? I can show you what is. I mean, this is like mixture of pattern matching and simple cake. What I'm benchmarking here. So do you think it will be like 2 times slower? Give your hand, raise your hand, or like 5 times slower? 10 times? What do you think? 10, 5 times, okay, good. And the answer is, it is slower, and the overhead introduced, so the difference between the baseline and the given representation between Java object-oriented like application and the Scala cake is around 300%, so it's like 4 times slower. Is it good? It is bad? It's up to you to decide, but for sure there is some overhead. And now probably it's time, maybe, because, okay, I can show you what I use here. So, so the code for ScalaSphere cake is really simple. So I got like the traits that represent each of the fit, like wisdom, dexterity, and strength. There is like the general trait that provides the traits they can use on later. There is a one to define total skill method. There is a one to define how the tree looks like. And finally, in the end, I bake the whole cake for each of the representation and run the costs. And as you can see, I'm not measuring the time to like build the thing. I'm only measuring the time to run the total skill method. So, maybe the pattern matching will be faster. Maybe there is other options that can like influence how the Scala code is whether it's slower or not. So let's see. So there's 4 things I want to measure. First one is like plain pattern matching to see whether it's like a cake that introduces overhead or the pattern matching itself. And this code is pretty similar to what I've shown for the ScalaSphere cake, but it just uses just the cake is removed. It's just simple pattern matching. There is I got this lambdas call that is basically a mixture of the object-oriented approach. So I got like, let's say, node, tree, and step, and skill as a classes with 1 trait. And instead of like creating a specialized class for each of the strength, each of the feet, I'm just passing the function that computes the current amount of the dexterity point, of the experience point required. So the tree looks like this, and like this. And I also want to measure things when we want to wrapping. Try. So this is also the pattern matching, but I think, okay, so maybe computation of the cost can return as an exception, and I don't want to bother with catch and try, so I'm using try, and then I will do a pattern, do a for comprehension on that try, and produce a value. So you will probably want to ask why I have to copy paste all these pieces of code, because I don't want to introduce yet another method call that is not required. I don't want to measure folding over the trait with one method call. So that's why in this benchmark class codes, I have to copy paste a lot. And the last thing is type classes. So type class, what I mean by type classes. So basically the tree looks the same, it's just no information there, any types, and I got a lot of implicits that can provide a class that can actually give me the total experience cost for each of the nodes. And then set up, and using this implicitly over here, I can compute the sum. So are you ready for the results? So let's start with pattern matching. So how do you think? What on which side of spectrum it will be, like closer to the object-oriented one? So it's the cake that introduced the overhead, or it's way closer to the cake itself? So it's the pattern matching that introduces overhead. So who thinks that this object, like the cake that introduces overhead? Okay, and the pattern matching? Okay, you are not sure. And the answer is it's pattern matching. If you can see here, like simple pattern matching, it's like almost 4 times slower. I got different, like comparing now with the Scala object-oriented style of code, it got slightly faster in that benchmark. So, but it tends to be pretty much the same as Java. So that is why the difference is maybe a little bit higher. But if you see the results like shown together, it's like the pattern matching is slightly faster than the code using cake. So it's the pattern matching that is really slow. I mean, maybe not really, it's just slower. And it was quite a surprise for me, because I was expecting that pattern matching is fast. And I was doing a lot of code with pattern matching, and now I probably have to rethink my ideas. But we will come to that later on. So now it's time to the wrapping in try. And for this one, I assume that it will be like, I don't know, 100 times slower, because we have to create a ton of garbage. There is lambdas all over the place, so it should be like super slow. It turns out it is slower, but let's say just 16 times. So I think for the safety of the tries, so for the more, like this kind of approach gives us like much more things than just a simple int in the end. So I think we can leave that kind of overhead. I was surprised it was that slow, because I was expecting that it would be like way over the one for the like 1 microsecond for the operation. So this was actually a positive surprise. And now let's see at lambdas. We're using lambdas everywhere, and the code that is using lambda is like it's object-oriented style. So it should be like, at least for me, if the lambdas are really cheap, it should be like closer to the object-oriented style. But on the other hand, I'm running, Scala 2.12 and Java 8. So Java should like the lambdas are quite new thing in the Java, so maybe they are not optimized that much. So I was a little bit worried. And it turns out that lambdas tends to have a lot of variance, so there's like a lot of noise. So there are like cases where it's quite slow, but later on, it's pretty much the same as the way like the pattern matching. So not bad. Only like 6 times, 7 times slower than the plain object-oriented approach. And the last one is the type classes. And here, I expected even more overhead than tries, because there is like for each method calls, I have to build this big structure of the classes. And for some reason, it will be like really slow. And it turns out this was one of the big surprises, that type classes are faster than pattern matching. For me, it was like eye-opening. I mean, maybe I have to like come back to, maybe we should lift more stuff to the type level, because it pays in the runtime. The only question that we might ask, like we want to ask, how, because this is like the dev code was really like well JIT. I mean, it was like the hot benchmark. I got like stable results, so JIT was not able to improve the performance even more. So how much time is required to get to the point when the type classes are that fast? We will see we will talk about that later on. But if you look at that, I mean, come on, type classes are faster than pattern matching, and it should be like the other way. So maybe we can improve the pattern matching. I don't know if you recall that we got in the pattern matching. We've got this quite a big of pattern matching. So there is a lot of computation. So to get to the wisdom skill, we have to compare like 8 other types. But we got like our structure is like nested. So we know that we got the trees, we know that we got the steps, skills. So maybe we can improve that. So maybe we can, nest pattern matchings to improve the performance. And this is where I can introduce a traits. And for each of the kind of the node, I'm first pattern match against the type of the node, and then pattern match against the concrete implementation. So how do you think? Will it improve the performance much? The answer is here. If you look at that, it's way over 1 millisecond per operation. So it's way slower. I mean, I was, what's going on there? I ran it multiple times, tried to check different things, and it always, like, the result was always the same. It is like, it was 38 times more overhead introduced. It's like, for me, it was, I tried to improve the code, and everything looks good on the paper, on the screen. Like, then I got the result of the benchmark, and it was like, oh, yeah, cool. Oh, whoa, what's going on? So maybe the traits are the problem. So what I did here, I just replaced the traits with the sealed abstract class. And the results are as we expected. It's like a lot of noise, the same as with the lambdas, but as you can see, for the nested, if you look at the lower percentile, like the 0.15 percentile, it's actually faster than the pattern matching. So we accomplished something here. So the approach maybe was not that bad, but it shows one thing. If you want to do is instance of, because pattern matching under the hood is transformed to is instance of, and you're doing it on the interfaces, it will be slow. But there is a thing that we like to do. I mean, I like to use my traits. So maybe there is a way to actually to optimize this kind of thing, especially if I got the sealed traits. So this is like the simple proof of concept, like really simple and stupid. So what I hear in the node, I introduced just an ID that basically represents the kind of the tree. So the kind of the node. So tree got its own step and skill. It's like 1, 2, and 4. So it's like binaries. And then instead of like in the first step, instead of pattern matching against the class of the node, I'm pattern matching against the ID. And then going further. So in this way, I still can use my sealed trait, because sometimes I cannot like extend from the class. And on the same time, maybe I will be as fast as before, as fast as the class. And the answer is, it is faster. It is, but it's also slower than if you use the classes. So there is a way to improve the performance of the nest of the case when you have to pattern match against the trait. And we can go and compare stuff like that for an hour, so I don't want to go further into that. In this link you can find on the project, when it's quite easy to actually add a new benchmark, and there is a harness in SBT to run and create generated charts for your benchmarks. So now I think we can come back to the question I asked around the type classes. As maybe you recall, they are like quite fast. What was that to say? So there is like, the overhead is like quite nice compared to this ugly object-oriented kind of approach. But the question I was like asking myself is like, how much time is needed actually to get there? How much time we need to actually to get to the point when our code is fast? And you know what? Let's try to benchmark it. So this is a kind of different benchmark, and I will not compare the results between two benchmarks like directly, because I shouldn't do this, because this is completely different measurement, even though I'm running the same operation. So here, instead of running like the benchmark for a given amount of time in computing operation, I'm running the benchmark for, let's say, for exactly 50 times in each iteration, and then measure the time for all those iterations. Why 50? I try to play with that number a lot, and when you got small numbers, you want to get a better size of the size of 1. But the problem is that there is no machines that can give you the times, the clocks, and how much you want to measure time. Its overhead is like around 30, 50, 100 nanoseconds. So what is more like it's hard to get the small thing, hard to measure the time for the small things. So that's why you have to like meet somewhere between the amount of data points during the warming up process and that actually be able to measure out of something useful. And I'm using a warm up here, but it's just one iteration of 20 runs because I want to eliminate all the noise from the class loading, starting, stop interpreting the stuff, this kind of thing. Because if I use that, like my chart looks like there was like something going on in the middle, and like from the 20, 30 iteration was like all flat, and I was unable to read anything from that. So here is our benchmark that we start our discussion today. It's like whether ScalaSphere approach is faster or slower than Java. So I don't know if you can see the legend quite well, but the red one is the object-oriented, and the green one is the pattern matching in the ScalaSphere, like with the ScalaSphere like cake. And maybe you can see, maybe you have to believe me that for between like in the first 500 iterations, the pattern matching is faster. And as you can see, to get to the this really well optimized state, it needs like over like almost the 4,500 of iterations, which means you can, if you like times it by 50, you will get like quite a lot of operations run. So the question is your code that you're running in your application is like way bigger, will ever get to that point that we optimize so well? I mean, Rory will talk more about how much time is taken to actually to JIT the ScalaSphere, but maybe it's not even possible. So let's draw all the benchmarks for the warm-up benchmarks for all the styles that we compared earlier. And it looks like that. I'm joking. Of course, this is a modern art. And the data science guys got this, I don't know if you've seen that, like this is a Pokemon on big data. So I think if you're benchmarking stuff, you can get like modern art of big data chart. Because it looks similar, because the actual chart looks like this. And it's only like 6 of the things. And I don't want to go into the much details here, because you can barely see that. And the thing is, like, the more you do benchmarking of the bigger stuff, this kind of noise that is your actual benchmark to normal stuff I have to work with. So let's go like through this kind of style. Like I think the tree can be readable. Maybe, I hope so. So the red one is, as again, the object-oriented one, and the blue one is pattern matching, and we compare that with the type classes. So as you can see, the type classes it's also quite fast to actually to get to the stable point, but then it's just slowly stay, like it's just slow. And maybe in the beginning, maybe there you can, like, if you see like even before like the first 500 iterations, there is something ongoing there, but still the pattern matching there is like beating everything. So if maybe the pattern matching is actually faster in applications, you have to benchmark that. Different kind of pattern matchings. I only take like first 500, like 600 iterations, because there is no point actually to talk about, because there is like, this is the place where pattern matching getting fast. And it's like, as you can see, it's getting fast, like really, really quickly. Like 13 operation, it's fast already. And with lambdas and wrapping in tries, it's pretty much the same story as with pattern matching. I mean, it gets to some point really quickly and then stays at that level, but the object-oriented approach is like optimized way and way more. So probably, I'm guessing, I don't know JIT that well, probably with the wrapping, or when we do lambdas, at some point we do not apply for the more optimization that JIT can do. So most of the slides, as I said, the code and everything that you want to play with, you can be found on my GitHub. So if you are interested and you want to like test whether, like, for example, the hit of this year, like tagless final approach to everything is fast or not, just go there and play. And short summary. So sadly, the Java-like boring kind of approach that we learned 20 years ago, it's still the fastest. Probably it's because the JIT is optimized, it's designed to optimize this kind of code. Type classes can be surprisingly well JITted, so it can work quite well. Probably JIT does realize that there is only one instance of the same object created, cache that object, and invoke the method. So that's my guess. Lambdas can introduce overhead that is acceptable, that we can work with, and it's not that much, especially for what lambdas give us. Pattern matching on trades is really slow. This was probably the most, like, the type classes was some surprise for me, but this was like, what was going on? Is my data, is my benchmarks right? But I think there is a way, there can be a way to actually to improve that. Maybe we should, like, because the pattern matching, like the rewritten pattern matching to the bytecode is really complicated because of the possibilities that we got there. But maybe we should actually look at that and try to improve that, even with the simplest hack as I showed, with that just have an integer in the traits that in pattern match against that integer. And everything is slow on the cold JVM. We know that. We all know that. But pattern matching seems to get optimized faster. So if you plan to, maybe for the cases like, I don't know, serverless approaches like Amazon Lambda, the pattern matching is the good way to go. It's up to you to decide. So fancier code styles in Scala introduce some overhead. It can be 5, 6, 10 times slower, but I think we can live with that. And it is probably not that big of a problem if you think about that in your business application, in your business code. Unless your code is doing mostly stuff like traversing, decomposing bigger structures, because this is where this kind of overhead of the operation matters most. And ScalaSphere, if you think about that, is doing mostly that. So maybe there is the thing that actually that makes ScalaSphere so slow, but I don't know. I don't trust anyone right now. I want to benchmark everything. This is like amazing quote from the SBT-JM8 plugin. Thank you so much. And I think I don't have time for questions, but I will be on the table so you can go grab me and ask some questions. Thank you so much.